Picture your hand, right now, reaching out towards something no bigger than a city. Something you could circle on foot in about the time it takes to watch a movie. That's the size we're talking about tonight. Not a planet. Not even close to a planet. Something you could walk around in an afternoon. And yet if you actually reached out and touched it, the very last thing that would happen to your hand and to you and to every atom that ever made up your body would happen faster than your brain could even register the word ouch. Before we get into exactly why and exactly how, drop a comment right now with your gut guess. Do you think you'd feel anything at all, even for a fraction of a second? Or does it happen too fast for pain to even exist? Hold on to your answer, because we're going to find out together whether you're right. And if you're the kind of person who wants to know exactly what your body would experience in its literal last instant of existing as a body, go ahead and subscribe, because this channel exists for exactly this kind of question. There's something almost funny about how casually we throw around the phrase, reach for the stars. It's meant to sound aspirational, ambitious, a little bit poetic. Tonight, we're going to take that phrase completely literally and walk through, step by step, with real numbers and real physics, exactly what it would cost you to actually do it. Not metaphorically, actually, because it turns out that somewhere out in our galaxy right now there are objects that used to be stars that are still, in a very real sense, made of star stuff, sitting quietly in the dark, spinning, waiting, and if you got anywhere near one, the universe would show you in about 2 seconds flat exactly how small the gap really is between ambitious and annihilated. Most of us walk around with a mental model of extreme that tops out at things like lava, or the vacuum of space, or maybe the inside of a volcano. Those are the go-to images our brains reach for when we try to imagine the worst possible place a person could end up. Falling into lava, as horrifying as it sounds, still leaves you as a recognizable, if rapidly disintegrating body for at least a few seconds, your nervous system still technically intact enough to register what's happening. The vacuum of space, contrary to what movies often show, wouldn't cause your body to explode, just to lose consciousness within about 15 seconds as the oxygen in your blood stops working properly. A genuinely survivable window if someone pulled you back in time. Even the inside of an active volcano, molten rock and all, is still fundamentally a chemical and thermal disaster. The kind of extreme environment that at least still plays by the same basic rules of physics and biology every other disaster on Earth plays by. Every single one of those things, lava, vacuum, volcanoes, would treat you almost gently compared to what we're about to walk through tonight. There is an object, several of them actually, scattered across our galaxy right now, silently spinning in the dark, that would not just kill you. It would kill you in a way that breaks the basic assumption every single one of those other disasters still respects, which is that you'd remain at some level a recognizable collection of atoms while it happened. Tonight, that assumption fails. And understanding exactly why it fails is going to take us somewhere genuinely strange, into physics that sounds more like a myth than a measurement. Except every single number we're about to walk through has actually been measured, calculated, and confirmed by real telescopes, pointed at real objects, sitting out there in the real universe at this very moment. So let's start with what this thing actually is, because the what matters just as much as the how, for understanding Why touching it would be so catastrophically different from touching anything else you've ever been warned about. A neutron star is what's left behind after a massive star dies. Not every star ends this way. Our own sun, when it eventually runs out of fuel billions of years from now, will swell up, shed its outer layers gently, and settle down into something called a white dwarf, a dense but relatively tame stellar remnant. But stars considerably more massive than our sun, somewhere north of about 8 times the sun's mass, die in a much more violent fashion. For most of their lives, these giant stars exist in a kind of delicate standoff, a war between two opposing forces that happens to be perfectly balanced for millions, sometimes tens of millions of years at a time. Gravity is constantly trying to crush the star inward, pulling every particle of it toward the center with relentless, patient force. Fighting against that collapse is the outward pressure generated by nuclear fusion happening in the star's core, where lighter elements are smashed together under incredible heat and pressure to form heavier ones, releasing enormous amounts of energy in the process. Energy that pushes outward hard enough to hold gravity at bay. Hydrogen fuses into helium. Once the hydrogen runs low in the most massive stars, helium fuses into carbon, and then, over successive stages, carbon into oxygen, oxygen into silicon, each stage burning faster and hotter than the one before it, and each stage buying the star less time than the last. Until you reach the elephant in the room, the one element that changes everything the moment it starts to accumulate: iron. Iron is the one element that, instead of releasing energy when fused, actually absorbs it. It sits at the very bottom of a kind of nuclear energy valley, the point where fusing elements together stops producing more energy and starts costing energy instead. The moment a massive star's core turns to iron, the fusion reactions that were holding the whole star up against its own gravity essentially switch off, all at once, across the entire core, sometimes within a matter of seconds after millions of years of stability. And gravity, which had been patiently waiting this entire time, wins instantly and catastrophically. The core, sometimes containing more mass than our entire sun, collapses in on itself in a fraction of a second, falling inward so fast and so hard that protons and electrons, the particles that make up ordinary atoms, get crushed together and forced to combine into neutrons, releasing a burst of ghostly particles called neutrinos so intense that it blows the rest of the star apart in one of the most violent events the universe produces: a supernova. For a few weeks, that single exploding star can outshine every other star in its entire galaxy combined, visible across distances of billions of light years to telescopes here on Earth. A final blinding farewell from a star that, just moments earlier by cosmic standards, had been quietly shining the same way it always had. And in the exact center of that explosion, in the tiny space where the core used to be, something extraordinary is left behind. All of that collapsed material, sometimes 1.5 times the mass of our sun, sometimes more, ends up packed into a sphere only about 12 miles across. Not 1,200 miles, not 12,000. 12? You could drive from one side of it to the other faster than most people's daily commute to work, if driving across a surface made of the densest material in the known universe were something your car could survive, which, as we're about to see in detail, it very much could not. Let's actually sit with that comparison for a second, because I don't think it lands properly the first time you hear it. Our Sun is about 865,000 miles across. A neutron star containing more mass than our Sun, sometimes considerably more, is about 12 miles across. Imagine taking every grain of sand on every beach on Earth, every rock, every mountain, every ocean's worth of water, all of Earth's entire mass, and compressing it down until it fit inside a sphere the size of a large stadium. That's roughly the compression ratio we're talking about when we go from an ordinary star to a neutron star. And unlike some analogies in this genre video, this one isn't exaggerated for effect. It's actually a fairly conservative way of describing what's really happening, because the true density involved is so extreme that almost any analogy you reach for ends up understating it rather than overstating it. Try picturing it a different way, one that might land a little harder. Take the entire city you live in, or the nearest big city to you, every building, every road, every car, every single person walking around inside it right now, and imagine compressing that whole city down until it disappeared entirely into a space smaller than a single grain of rice. That's roughly the scale of compression happening when an ordinary star's core becomes a neutron star. Except we're not compressing a city, we're compressing something with more mass than our entire Sun, which itself contains more than 300,000 times the mass of Earth. There isn't really a clean, satisfying way to picture this that doesn't eventually break down, because human intuition, quite reasonably, was never built to process compression ratios like this one. Our brains evolved to judge distances across a savanna, weights we could lift, sizes of animals that might eat us. None of that evolutionary toolkit was built with neutron stars in mind. Which is exactly why every analogy you'll hear tonight, including the ones I'm about to give you, should be understood as a ladder to help you climb toward the real number, not a perfect substitute for it. Here's a number that I think captures the sheer weirdness of this better than almost anything else. A neutron star is so dense that if you scooped out a piece of it the size of a single sugar cube, just picture a normal cube of sugar sitting on a kitchen counter, that tiny cube would weigh somewhere in the neighborhood of 1 billion tons. To put that in perspective, that's roughly comparable to the combined weight of every single human being currently alive on Earth, packed into a chunk of matter you could hold in the palm of your hand. If your hand and the rest of your body and the planet underneath you could somehow survive holding it, which they absolutely could not, for reasons we're about to get into. This density comes from something genuinely strange happening at the quantum level. Ordinary matter, the stuff you and I and everything around us is made of, is almost entirely empty space. An atom is mostly nothing, with a tiny, dense nucleus surrounded by electrons orbiting at relatively enormous distances. The same way a fly buzzing around the inside of a cathedral would represent the electron's distance from the nucleus if the nucleus were the size of a marble sitting on the cathedral floor. If you could somehow remove all of that empty space from every atom in your body, all of it, every gap between every nucleus and every electron cloud, you personally would shrink down to a speck far too small to see with the naked eye, while still containing every bit of the mass you currently have. That's how much of you, in terms of pure volume, is actually just empty space held open by electromagnetic forces, not solid matter at all. It's a strange thing to sit with, honestly, given how solid everything around you feels right now. the chair beneath you, the ground under your feet, your own hands. Every single one of those things is, by volume, overwhelmingly nothing. Empty space held rigid by forces you never think about, doing their job so quietly and so reliably that solid feels like an obvious, unquestionable fact about the world rather than the outcome of an ongoing, active balancing act between opposing forces. Neutron star material doesn't work that way. The crushing force of the supernova collapse was strong enough to eliminate almost all of that empty space, squeezing electrons and protons directly into each other until they merged into neutrons, and packing those neutrons together edge to edge, the same way the protons and neutrons inside an ordinary atomic nucleus are already packed. Except now that packing extends across an entire 12-mile sphere instead of being confined to a nucleus too small to see even with the most powerful microscopes we've ever built. In a very real sense, an entire neutron star is one single, enormous atomic nucleus, held together not by the nuclear forces that hold ordinary nuclei together, but by the sheer, overwhelming crush of its own gravity. Physicists sometimes describe this by saying a neutron star is the closest thing in the observable universe to a giant atomic nucleus you could actually see from space, if you had a telescope powerful enough and were foolish enough to want to look directly at one up close. Now, here's where we start getting into the part of tonight's story that actually answers the question in the title. Because everything we've covered so far is just the setup. The real question is what happens as you approach this thing, and the honest physics-based answer is that you never actually get the clean, simple experience of touching it at all, in the way you might touch a hot stove or a block of ice. Long before your hand, or your spacecraft, or anything else made of ordinary matter gets anywhere near the actual surface, something called a tidal force takes over completely, and it's worth walking through exactly what that means, because it's the actual mechanism of death here, not the surface itself. Tidal force is something you've technically already experienced in an extremely gentle, harmless form every single day of your life, without ever noticing it. It's the same basic phenomenon that causes ocean tides here on Earth. The moon's gravity pulls slightly harder on the side of the Earth facing it than on the far side, because gravity weakens with distance and the near side is simply closer. That difference in pull, small as it is across a planet the size of Earth, is enough to stretch the oceans very slightly into an oval shape, creating the tides that rise and fall along every coastline on the planet. It's a generally tiny effect when you calculate the actual numbers involved, a difference measured in millionths of the moon's total pull, and yet it's still strong enough to move literal oceans twice a day forever, which should already give you a hint about how seriously we need to take this force once we start scaling it up. Now take that exact same basic idea, a difference in gravitational pull between one side of an object and the other, and scale it up by an almost unimaginable factor. Because a neutron star doesn't just have strong gravity. It has gravity so strong, packed into a radius so small, that the difference in pull between a 0.1 meter away from its center and a 0.10 meters away from its center isn't a gentle ocean tide kind of difference. It's a difference violent enough to rip apart the strongest materials humans have ever engineered, long before you'd get anywhere near the actual surface. This is the key thing that makes tidal forces so uniquely dangerous around compact objects like neutron stars and black holes compared to ordinary planets and stars. Around a normal planet, you have to get impossibly close, closer than the object's own physical surface allows, for tidal forces to matter at all, which is why nobody worries about being torn apart by Earth's gravity, even standing right at sea level. But a neutron star packs planet and a half worth of mass into a sphere the size of a city, which means you can get shockingly close to its center in absolute terms, while still being nowhere near its actual physical surface, and tidal forces scale with how close you are to the center, not how close you are to the surface. That mismatch, all that mass concentrated into such an unbelievably small space, is exactly what turns an ordinary, boring force you've been feeling your whole life into an instrument of near-instant destruction. Let's put real numbers on this, because vague descriptions like incredibly strong don't really do justice to what we're talking about. The surface gravity of a typical neutron star is somewhere in the range of 100 billion to several trillion times stronger than the gravity you're feeling right now. Sitting wherever you are, reading or listening to this sentence, not 100 times stronger, not 1,000 times stronger, somewhere between 100 billion and several trillion times stronger, depending on the exact mass and size of the specific neutron star in question. To give that number some kind of human scale anchor, if Earth's gravity is what currently keeps your feet on the ground with a pull we casually call 1g, standing on the surface of a neutron star would feel like experiencing over 100 billion Gs, an amount of force so far beyond what any human body, or honestly any physical structure at all, could withstand, that the concept of withstanding it stops applying in any meaningful sense. For comparison, fighter pilots pulling extreme maneuvers might briefly experience somewhere around 9 Gs before blacking out, and that's already considered close to the outer edge of what a trained, conditioned human body can tolerate for even a few seconds, with special pressurized suits designed specifically to keep blood from rushing away from the brain. A car crash, the kind severe enough to be fatal, might involve forces in the range of 50 to 100 Gs for a fraction of a second. Even the most extreme forces humans have ever deliberately survived under controlled conditions. Test pilots and rocket-led volunteers pushing the absolute edge of what a strapped-in, braced human body can endure tend to top out somewhere in the range of 40 to 50 Gs based on historical test records, and even those brief exposures leave lasting injuries, burst blood vessels in the eyes, temporary blindness, sometimes broken bones from the sheer force of the restraints holding the body in place. We are talking about a force here that is roughly 1 billion times larger than the crash that would already be instantly fatal to a human being. And that's on the conservative end of the range for an ordinary neutron star. There simply isn't a meaningful way to describe what 100 billion Gs does to a human body using the normal vocabulary we reach for when describing injuries, because injury implies some part of the original structure survives the event long enough to be classified as injured. At this scale, that entire premise breaks down instantly. And here's the part that actually determines the answer to tonight's title question. Because gravity gets weaker the further you are from an object. And because a neutron star's gravity is so overwhelmingly strong to begin with, the difference in pull between the near side and far side of your body doesn't wait until you're brushing up against the surface to become deadly. Based on calculations astrophysicists have run on exactly this kind of scenario, a human body, or really any object held together by ordinary chemical and structural bonds, would begin experiencing lethal tidal stretching, the technical term astrophysicists sometimes only half-jokingly call spaghettification, while still thousands of kilometers away from the neutron star's actual surface. Thousands of kilometers. Not meters, not the last few feet before contact. You would be torn apart, stretched into an impossibly thin, elongated stream of what used to be atoms, while you were still comfortably farther from the star than the distance separating most major cities on Earth from each other. Here's what that would actually feel like, or rather, here's what it would look like, since the feeling part gets complicated fast, and we're going to be honest about exactly where the science gets uncertain in just a moment. As you fell closer, the gravitational pull on the part of your body closest to the star would become measurably, then dramatically, then catastrophically stronger than the pull on the part of your body farthest away. Your feet, if you were falling in feet first, would accelerate away from your head at a rate that increases every single moment, stretching your body first gently, the way a rubber band stretches when you first pull on it, then violently past the point where any bone, muscle, or connective tissue could possibly hold together. Based on the numbers we just walked through, most calculations suggest this process, from the first noticeable stretch to complete structural failure of the human body, would happen over a span of a few tenths of a second to at most a couple of seconds, depending on exactly how far out the tidal forces first become strong enough to overcome your body's structural integrity, which itself depends on the specific mass and size of the neutron star you happen to be falling toward. It's worth saying plainly that this specific time frame is an inference drawn from the same tidal force equations used to model tidal disruption events around black holes, applied here to a human-sized object rather than a star, so while the underlying physics is solid, the precise number of tenths of a second is a reasonable estimate rather than a figure anyone has ever directly measured. The broader point, that the process unfolds in a handful of seconds at most rather than minutes or hours, holds up regardless of exactly which tenth of a second the failure actually begins in, and it's that broader point, not the exact decimal, that the rest of tonight's story rests on, so nothing that follows depends on pinning that number down any more precisely than physics currently allows. To put that timeline in perspective, a couple of seconds is roughly how long it takes to blink twice, or to say the words "what's happening" out loud at a normal speaking pace. That's the entire window, start to finish, between everything is fine and nothing resembling a human body exists anymore. Compare that to something like a car crash, which, as violent and sudden as it feels, actually unfolds over a slightly longer span, giving the body at least some structural continuity to sustain damage that doctors can later categorize, treat, or at least identify. What we're describing tonight doesn't leave behind that kind of aftermath. There's no wreckage to examine, no body to recover, not because everything gets vaporized in a fireball the way movies often depict, but because the process is fundamentally geometric rather than explosive, a stretching rather than a shattering, which somehow makes it feel even stranger to think about than an explosion would. It's worth comparing this to something a little more familiar too, just to anchor the scale properly. If you've ever watched someone stretch a piece of taffy or pizza dough, pulling it slowly at first, then faster, until it thins out into a long, delicate strand right before it finally snaps, you've already seen a gentle, kitchen counter version of the exact same physical process that would happen to a human body approaching a neutron star, just compressed from a leisurely few seconds of stretching dough into a violent couple of seconds of stretching bone, muscle, and tissue. And instead of finally snapping cleanly the way dough does, continuing to thin out atom by atom, layer by layer, well past the point where any material humans have ever studied would normally be expected to hold together at all. I want to pause here and be honest about something, because this is exactly the kind of place where a video like this could either get sloppy or get genuinely interesting, and I'd rather it be the second one. Whether you would consciously feel pain during those crucial fractions of a second is a genuinely harder question than the raw physics of the stretching itself. And it's worth separating those two things clearly rather than blurring them together the way a lot of pop science content tends to. The physics of tidal disruption, the actual forces, the actual timescales, the actual sequence of your body's structural failure is about as well understood as any scenario in this entire field, calculated using the same equations of general relativity that have been tested and confirmed in dozens of other contexts, from the bending of starlight around our own sun to the exact timing of signals from orbiting satellites. That part isn't speculative, but what your nervous system would actually register, whether pain signals could even propagate through a body being pulled apart at that speed, whether your brain would have time to process anything at all before the specific tissues responsible for processing pain were themselves torn away from the rest of your nervous system, is a genuinely different kind of question. One that ventures into territory neuroscience and physics haven't fully mapped together, because thankfully nobody has ever actually been available to report back on the experience. Based on how quickly this kind of tidal disruption unfolds though, and based on how nerve signals travel at finite measurable speeds through the human body, roughly on the order of 100 meters per second for the fastest nerve fibers we have, a reasonable inference is that any pain signal generated by the initial stretching would have, at absolute most, a fraction of a second to reach your brain before the specific connections needed to process it had themselves been pulled apart, which suggests, though it can't be stated with total certainty, that the experience would be mercifully brief even if it wasn't entirely painless. It's worth being honest that this is one of the few places in tonight's story where we're extending well-established physics into territory neuroscience hasn't fully mapped, and where a more cautious phrasing based on what we know about nerve conduction it's reasonable to infer fits the evidence better than a flat, confident claim either way. What's left after those first couple of seconds is something almost impossible to picture accurately, and yet astrophysicists have a genuinely useful analogy for it, one they didn't invent for shock value but actually use in real published research papers, because it turns out to be the most accurate way to describe the geometry of what happens. Your body and everything that used to make it up would be stretched into an incredibly long, incredibly thin stream of matter, essentially a strand of what used to be a person, potentially stretching out over a distance of many kilometers, while getting thinner and thinner as it falls. the same way pulling taffy stretches it longer while making it thinner at the same time. This is the exact same process, scaled up almost beyond comprehension, that astronomers have actually observed happening to entire stars that wander too close to black holes. Events called tidal disruption events, which show up in telescopes as a sudden, dramatic flare of light as a star gets stretched into a long, glowing filament of gas before spiraling into oblivion. Astronomers have caught several of these events happening in real time over the past couple of decades, using space telescopes and ground-based observatories to watch, from safely across the universe as an entire star, sometimes similar in size to our own Sun, gets pulled apart by the gravity of a supermassive black hole at the center of some distant galaxy. The star doesn't just vanish, it stretches, exactly the way we've been describing, into a long, glowing ribbon of gas, half of which gets flung outward into space while the other half spirals inward, heating up as it falls until it briefly shines as bright as the entire galaxy surrounding the black hole. A final, brilliant scream of light from a star that, moments before, had been living an ordinary, unremarkable stellar life, not unlike our own Suns. We've watched this exact process happen to objects the size of stars. The physics scales down consistently to explain what would happen to something the size of a human body approaching a neutron star instead, just compressed into a smaller, faster, more localized version of the same fundamentally violent process, unfolding over seconds instead of the days or weeks it takes for an entire star to be consumed. And here's the detail that I think deserves real attention before we go any further into this story, because it changes the entire shape of the question the title of tonight's video is actually asking. If tidal forces do all of this thousands of kilometers before you'd ever reach the actual surface of the neutron star, then the honest answer to what happens if you touch a neutron star is that you don't, in any meaningful sense, get the chance to. The word touch implies a moment of contact between two intact things, your hand and a surface. But by the time whatever remains of you actually reaches that surface, you have already ceased to exist as anything resembling a hand, or a body, or a person, for what is, by any measure of ordinary human experience, a very long time already, even though the entire process, start to finish, unfolds in less time than it takes to read this sentence out loud. This is worth sitting with for a moment, because it's exactly the kind of detail that separates a genuinely accurate answer from the kind of vague, dramatic answer you might get from a movie or a video game. Popular culture tends to imagine touching something dangerous as a single, discrete moment, fingertip meets surface, and then something bad happens as a direct consequence of that contact. What we're actually describing tonight is a process that begins acting on you well before any contact occurs at all. A kind of destruction that reaches out ahead of the object itself, dismantling you at a distance the way an unseen current can pull a swimmer under long before they ever reach the rocks they were trying to avoid. The neutron star, in a very real sense, doesn't need you to touch it. It just needs you to get close. And close, on the scale we're discussing tonight, still means thousands of kilometers of empty space separating you from anything you could call a surface. Before we get to what actually happens at the moment of contact, though, it's worth taking a short detour to answer a question you might already be asking yourself. How do we even know any of this? We've never sent a probe anywhere near a neutron star, obviously, and for very good reason given everything we've just walked through. So where do these numbers actually come from? There's one more number worth understanding before we get to that detour though, because it ties everything we've covered so far into a single, almost unbelievable statistic: escape velocity. Escape velocity is simply the speed you'd need to reach in order to break free of an object's gravity entirely. The same concept that determines how fast a rocket needs to travel to leave Earth behind. For Earth, that number is a little over 7 miles per second, fast but well within the capabilities of modern rocketry. For our Sun, despite its enormous mass, the escape velocity is still a relatively modest 380 miles per second. Because the Sun, while massive, is also spread across a huge volume, which weakens its surface gravity compared to what you'd get if that same mass were compressed down small. For a neutron star, escape velocity climbs to somewhere between roughly a third and over half the actual speed of light, depending on the specific star's mass and radius. Meaning that to escape a neutron star's gravity once you were sitting on its surface, you would need to be moving at a meaningful fraction of the fastest speed anything in the entire universe is physically permitted to travel. Light itself, if it happened to be emitted from very close to the surface at just the wrong angle, can actually get bent back down onto the star by gravity alone, curving through space the way a ball thrown too gently curves back down to Earth. An effect so extreme that from certain vantage points you could theoretically see the back of a neutron star's own surface, its light bent all the way around the curve of the star toward your eyes. A genuinely bizarre visual effect that has actually been modeled and confirmed using the same general relativity equations that govern everything else we've discussed tonight. Imagine standing close enough to a basketball to somehow see the entire surface of it at once. Front, back, and sides all folded into view simultaneously, without the ball actually being transparent. That's roughly the visual experience light bending this extreme would produce if you were somehow able to survive long enough and from a safe enough distance to actually look. The answer is one of the more remarkable detective stories in modern astronomy. Neutron stars were first predicted on purely theoretical grounds in the 1930s. Years before anyone had any direct evidence they actually existed, by physicists working through the equations of what would happen to a collapsing stellar core, essentially solving the math before nature had shown its hand. It took until 1967 for the first real observational evidence to show up when a graduate student named Jocelyn Bell Burnell, working with a radio telescope specifically built to study a completely different phenomenon, noticed an incredibly regular, precise pulse of radio waves coming from a fixed point in the sky, repeating with a consistency so exact that some of the astronomers on her team, briefly, half-jokingly, wondered if they'd stumbled onto a signal from an alien civilization, nicknaming the source LGM-1 for Little Green Men, before the far stranger and far more wonderful natural explanation became clear. Picture what that moment must have actually felt like, sitting in front of long rolls of chart paper, night after night, watching this strange, perfectly regular blip appear at the exact same spot in the data, over and over, with a precision that nothing natural was supposed to produce. It's easy, looking back with the benefit of hindsight, to treat this discovery as an inevitable, straightforward confirmation of a theory that already existed. but at the time, sitting there with that data. It must have felt like standing at the edge of something genuinely unknown, choosing between two wildly different explanations. One involving an alien civilization deliberately signaling across the stars, and one involving a kind of star nobody had ever directly confirmed existed. What they'd actually found was a rapidly spinning neutron star. Its intense magnetic field sweeping a beam of radio waves around like a cosmic lighthouse, sweeping past Earth with every single rotation. Precise enough that some of these objects keep better time than many atomic clocks built by human engineers. Since then, astronomers have identified well over 3,000 of these spinning neutron stars called pulsars scattered across our galaxy and used the incredibly precise timing of their pulses, combined with careful measurements of their mass, their radius, and how they bend and warp the light around them, to build the exact numbers we've been walking through tonight. Every figure in this video, the density, the gravity, the escape velocity, comes from real telescopes, pointed at real objects over decades of patient, careful observation, not from speculation or guesswork. That's actually one of the things I find most remarkable about this whole topic, and it's worth sitting with for a second before we move on. Everything we've walked through tonight, the sugar cube-sized piece of star weighing as much as all of humanity, the tidal forces strong enough to dismantle a person thousands of kilometers before contact, the light bending back around the star's own curve, none of it comes from a science fiction writer's imagination. It comes from decades of astronomers pointing increasingly sensitive instruments at the sky, catching faint pulses of radio waves, timing them down to fractions of a millisecond, and painstakingly working out the physics required to produce a signal that precise from an object that small, that far away. In a strange way, neutron stars are proof that reality, left to its own devices, is stranger and more inventive than almost anything we could dream up on purpose. Now, back to the question that actually matters for tonight's title. We've established that you never really get a clean moment of touching a neutron star because tidal forces do their work long before contact. But let's set that aside for a moment, purely as a thought experiment, and ask what would happen if, somehow, through some hypothetical shielding or some deliberately simplified version of this scenario, matter actually did reach the star's surface intact. What would the neutron star itself do with it? Because the surface isn't just a wall you'd smash into. It's an active, extraordinarily hot, extraordinarily magnetized environment that would do something to any matter reaching it. Something genuinely strange. Something that involves energies far beyond anything produced by ordinary nuclear reactions, including the ones powering our own sun, releasing in the process an amount of energy that would make even the violence of the tidal disruption we just walked through look almost gentle by comparison. It's worth taking a breath here before we get into that final piece, because everything we've covered so far, the density, the crushing gravity, the tidal forces stretching a body apart thousands of kilometers out, is honestly the part of this story most people expect once they hear the word neutron star. What comes next? The actual physics of contact itself. The magnetic fields powerful enough to distort the very shape of atoms, the rotation speeds fast enough to make a 12-mile sphere spin hundreds of times every single second, is the part that tends to surprise people even after they think they've already grasped how extreme these objects can get. It turns out that everything we've walked through tonight so far is really just the entrance fee. The strangest part of this story is still ahead. Think about everything we've covered so far as the physics of getting there. The size, the density, the crushing weight of a sugar cube's worth of neutron star material, the tidal forces reaching out thousands of kilometers ahead of the surface to do their work long before contact ever becomes possible. That's the journey. What we haven't touched yet is the destination itself. The actual surface, spinning, glowing, wrapped in a magnetic field so intense it would make the strongest magnets human engineers have ever built look like a child's refrigerator magnet by comparison. We haven't talked about what that surface is actually doing, moment to moment, or what it would do to any matter unlucky enough to actually make contact with it. Hypothetically speaking, if we set aside for a moment everything we just learned about tidal forces getting there first. We haven't talked about how fast some of these objects spin. Fast enough that a point on their equator moves at a meaningful fraction of the speed of light, whipping around a complete rotation hundreds of times every single second. And we haven't talked about the deepest, strangest question of all, the one that ties this entire topic back to something almost philosophical. What does it actually mean that objects like this exist at all? Spinning quietly in the dark corners of our own galaxy, holding physics at its absolute unforgiving extreme, entirely indifferent to whether anyone ever notices them or understands what they represent. All of that, the magnetic fields, the impossible rotation speeds, the actual physics of contact, and what this whole topic ultimately says about the universe we happen to be living in, is exactly where we're headed next, and I promise you, if tonight's first half already reshaped how you think about extreme, what comes next is going to reshape it again. Because it turns out even the tidal forces we just spent this entire conversation on aren't actually the strangest thing a neutron star has to offer. What waits at the surface itself and in the space immediately around it involves physics that pushes past even general relativity and into territory where our best current theories start to strain at their own edges, describing behavior that's been observed, measured, and confirmed, but that still manages to feel, even to the physicists who study it for a living, genuinely stranger than fiction. Stick around, because that's exactly where we're picking things back up, with the same star, the same 12-mile sphere of impossible density, but a completely different kind of danger waiting at its surface. A neutron star's magnetic field isn't just strong. It's strong in a way that breaks the normal relationship between strong and familiar almost completely. Earth's own magnetic field, the one responsible for making a compass needle point north, the one that shields us from the worst of the sun's radiation, measures about half a Gauss at the surface. A unit physicists use to describe magnetic field strength. A basic refrigerator magnet, the kind holding a grocery list to your fridge door right now, measures somewhere around 100 Gauss, already 200 times stronger than the entire planet's magnetic field. An emery machine, one of the strongest magnetic fields most people will ever encounter directly, reaches somewhere around 10,000 Gauss, powerful enough that hospitals maintain strict safety zones to keep loose metal objects, oxygen tanks, wheelchairs, even pens, from becoming dangerous projectiles the moment they get too close. There are documented cases of exactly this happening. Oxygen tanks and mop buckets pulled clean across a room and slammed into the machine, which should already give you a sense of just how much respect a mere 10,000 Gauss commands, before we even get to the numbers that actually matter for tonight. It's worth pausing on that comparison for a second, because the jump from an emery machine to a neutron star isn't a gentle climb up a gradual slope. It's closer to a cliff. Every magnet you've ever encountered in your entire life, every fridge magnet, every Murray scanner, every industrial electromagnet used to lift scrap cars in a junkyard falls somewhere within a range that never exceeds a few tens of thousands of Gauss. A range narrow enough that engineers can describe the entire spectrum of human magnetic technology using a single, modest set of units without ever needing to reach for anything more dramatic. A typical neutron star's magnetic field measures somewhere in the range of 1 trillion Gauss, not 1,000 times stronger than an emery machine, not 1,000,000 times stronger. 1 trillion Gauss, meaning the field is roughly 100 million times more powerful than the strongest continuously operating magnets human engineers have ever managed to build on Earth. Magnets that already require massive superconducting coils, liquid helium cooling, and enormous amounts of electricity just to sustain a fraction of that strength for laboratory experiments. And that's for an ordinary neutron star, the unremarkable common variety. There's a rarer, even more extreme subtype called a magnetar, where the magnetic field climbs even further, up to somewhere between 100 trillion and 1,000 trillion Gauss, based on measurements astronomers have taken from a specific class of these objects using X-ray telescopes. Only about 30 of these objects have been confirmed so far out of the thousands of neutron stars astronomers have catalogued, which tells you something about just how rare this particular extreme really is, even among objects that are already, by any ordinary standard, unimaginably extreme to begin with. At that level of magnetic intensity, the field itself contains so much raw energy that it starts to become the dominant force in the entire system, more influential to the star's behavior than gravity, more influential than its own internal heat, driving sudden violent eruptions called starquakes, where the star's rigid outer crust cracks under magnetic strain the way an eggshell cracks under pressure, releasing, in the most powerful of these events ever recorded, more energy in a fraction of a second than our own sun produces in 100,000 years. One such event, recorded by satellites in December of 2004 from a magnetar roughly 50,000 light-years away, released so much gamma radiation in a fraction of a second that it measurably disturbed the upper atmosphere of Earth, briefly ionizing part of our own planet's atmosphere from a source clear on the other side of the galaxy. A genuinely humbling reminder of just how much energy these starquakes actually release. Here's why this matters so much for understanding what actually happens to matter at the surface. And it's a piece of physics that sounds almost like science fiction until you realize it's been directly confirmed through decades of X-ray and radio observations. A magnetic field this powerful doesn't just push and pull on metal objects the way a normal magnet does. It fundamentally distorts the shape of atoms themselves. In an ordinary atom, electrons orbit the nucleus in relatively round, spread out clouds, their shape determined by a balance between the electrical attraction pulling them toward the nucleus and their own quantum mechanical tendency to spread out. Every atom in your body, in the air around you, in every object you've ever touched, keeps this same basic round shape because the electromagnetic forces holding ordinary matter together are, on Earth, always operating within a fairly narrow, predictable range. Near the surface of a neutron star, the magnetic field is so overwhelmingly strong that it completely overpowers this normal balance. Electrons get squeezed into incredibly narrow, elongated shapes, stretched along the direction of the magnetic field lines like thread being pulled taut, until atoms stop looking anything like the round, familiar structures every chemistry class teaches. Based on detailed calculations physicists have run using quantum mechanics under these extreme field conditions, atoms near a neutron star's surface become long, needle-thin cylinders, sometimes hundreds of times narrower than an ordinary atom's normal width, packed together into structures that behave more like tiny rigid rods than the soft round atoms making up literally everything you've ever touched, seen, or been made of. Some theoretical models even suggest that under a strong enough field, hydrogen atoms could link together into long molecular chains that behave less like a gas and more like a solid, needle-shaped crystal. An entirely different phase of matter with no equivalent anywhere else in the observable universe outside these extreme environments. This means that ordinary chemistry, the entire elaborate system of bonds, reactions, and molecular structures that builds everything from water to DNA to your own body, simply cannot exist in this environment, in any form remotely resembling what we understand chemistry to be. The electron behavior that allows atoms to share electrons form bonds, and build the staggering complexity of organic molecules depends entirely on electrons having enough freedom to interact with neighboring atoms in specific, predictable ways. Crush those electron clouds down into narrow, rigid cylinders locked rigidly along magnetic field lines, and that entire foundation collapses. Whatever exists at a neutron star's surface isn't chemistry, as any part of the universe we're familiar with understands the term. It's a different regime of matter entirely, one where the rules governing how atoms interact have been rewritten from the ground up by a magnetic field so strong it makes the electrical forces holding ordinary chemistry together look almost negligible by comparison. So let's go back to that stream of matter we left off with earlier, the stretched, thinned remnant of whatever fell toward the star, already reduced by the tidal forces we walked through into something no longer resembling atoms, molecules, or anything with a recognizable chemical identity. As that material actually reaches the star's crushing magnetic field and gravitational pull near the surface, whatever remaining structure survived the tidal stretching gets subjected to this same field-driven distortion. And then, immediately afterward, the crushing density itself. Protons and electrons, if any coherent version of them, still exists by this point, get forced together by the sheer gravitational pressure merging into neutrons, the same fundamental transformation that created the neutron star in the first place during the original supernova collapse. It's worth pausing on how strange this actually is, philosophically, even setting aside the sheer violence of it. In a very real sense, the neutron star is doing to your matter in a fraction of a second exactly what a dying star's own collapsing core did to itself over the course of that same fraction of a second, billions of years earlier. The same basic physical process, protons and electrons crushed together into neutrons under overwhelming pressure, that created every neutron star in the sky is the exact process that would convert whatever remained of you into more of the same material. In other words, whatever falls into a neutron star doesn't just get destroyed. It gets converted at the most basic subatomic level into the exact same kind of matter making up the star itself, joining the crust or ocean of neutron-degenerate material already there, indistinguishable at that point from every other neutron packed into that 12-mile sphere. This transformation releases an amount of energy that's genuinely difficult to overstate. And it's worth walking through exactly why, because the number involved connects directly back to some of the most important astrophysics we actually observe happening in real neutron star systems, not just hypothetical scenarios like the one we've been building tonight. When matter falls onto a neutron star from a great distance, it picks up enormous speed along the way, converting gravitational potential energy into kinetic energy exactly the way a ball rolling downhill picks up speed, except a neutron star's gravity is so overwhelmingly strong that infalling matter can be accelerated to a meaningful fraction of the speed of light by the time it reaches the surface. When that matter then slams into the surface and comes to a stop, all of that kinetic energy has to go somewhere, and based on detailed calculations astrophysicists have worked out for real observed systems, this process can convert somewhere around 10 to 20% of the infalling matter's total rest mass energy directly into radiation, mostly in the form of intense X-rays. To put that number in perspective and understand why it matters so much, nuclear fusion, the process powering our own sun and every other ordinary star, converts less than 1% of the mass involved into energy, roughly 0.7% for the specific hydrogen to helium fusion happening in our sun's core right now. Matter falling onto a neutron star can be roughly 10 to 20 times more efficient at generating energy than the exact same amount of matter being burned as nuclear fuel inside a star. Think about what that actually means for a moment. The same handful of hydrogen atoms that might power a star's fusion reactions for millions of years, if instead simply allowed to fall from a distance onto a neutron star's surface, would release more usable energy in that single moment of impact than an equivalent amount of nuclear fuel could release through fusion over an enormously longer span of time. Gravity, in this specific and admittedly extreme circumstance, turns out to be a more efficient engine for converting matter into energy than the nuclear furnace at the heart of every star in the sky. This isn't a hypothetical calculation dreamed up for a video script. Astronomers observe this process happening in real binary star systems throughout our galaxy right now, where a neutron star's powerful gravity strips material away from a companion star, and that material spirals inward and crashes onto the neutron star's surface, producing some of the brightest, most energetic X-ray sources visible to our telescopes, bright enough to be detected from clear across the galaxy, powered by nothing more exotic than ordinary matter falling the last few miles onto an extraordinarily dense, extraordinarily compact surface. So, if you were the one falling, And by this point in tonight's story, that's a genuinely hypothetical you, since the tidal forces would have already finished their work thousands of kilometers earlier. The actual moment of contact wouldn't look like a body hitting a surface. It would look, from a safe distance, like a brief, intensely bright flash of X-rays. The gravitational energy of your fall converted almost instantly into radiation, releasing more energy from that small amount of matter than most nuclear reactors on Earth produce across their entire operational lifetime. An observer watching from a safe distance, equipped with the right instruments, wouldn't see anything resembling an impact, a splash, or an explosion in the way those words usually imply. They'd see a sudden, sharp spike in X-ray brightness, gone again within a fraction of a second, indistinguishable in principle from the thousands of similar flashes astronomers already routinely observe from real neutron star systems feeding on ordinary matter stripped from companion stars. Whatever atoms used to make up your body would cease to exist as atoms entirely. Converted first into a stream of bare subatomic particles by the magnetic field, then crushed into neutrons by the star's density, then finally absorbed into the vast uniform sea of neutron degenerate matter making up the star's crust, indistinguishable from that point forward from every other neutron already there. There would be no remains, not because everything gets vaporized dramatically, but because the concept of remains requires some structure to persist that could be identified as belonging to you, and by the time contact actually happens, that structure has already been erased, twice over, first by tidal disruption, then by magnetic and gravitational transformation well before the flash of X-rays even had time to travel outward and announce that anything had happened at all. Now, earlier tonight, I asked you to guess whether you'd feel anything at all in that final moment, even for a fraction of a second, or whether it happens too fast for pain to even exist. Based on everything we've walked through, here's the honest, complete answer. One that respects both what the physics can tell us with confidence and what it genuinely can't. The tidal disruption itself, the stretching, would likely happen faster than a complete pain signal could travel from your body to your brain and be consciously processed, based on how nerve conduction speeds compare to the timescale of the disruption, which suggests, though it can't be stated with absolute certainty, that any subjective experience of pain would be either extremely brief or effectively non-existent. But here's the detail that I think actually deserves more attention than it usually gets in this kind of discussion. Your death wouldn't happen at the surface at all. It would have already happened, completely and irreversibly, in the moment tidal forces first exceeded what your body could structurally withstand, thousands of kilometers before the actual surface, and everything after that. The magnetic distortion, the neutron conversion, the flash of X-rays would be happening to matter that used to be you, not to you, in any sense that still involves a functioning nervous system capable of experiencing anything at all. If your guess was too fast to feel it, you were right, but for a reason that might be even stranger than you expected. Not because the moment of death is instantaneous, but because it happens so far removed from the part of the story most people imagine as the end that there's essentially no version of this scenario where a conscious you experiences the actual surface at all. I think this detail matters more than it might seem at first, because it changes what the word touch was ever actually going to mean in this entire scenario. Most people hearing tonight's title probably pictured something like reaching a hand out and making contact with a glowing, impossibly dense surface, a single, dramatic moment where cause meets effect. What the physics actually describes is something closer to a long, cascading sequence of destructions, each one happening to something that's already less you than the version that came before it, stretching from the first moment tidal forces became noticeable all the way down to a final flash of X-rays marking the conversion of your last remaining atoms into raw neutron matter. There's no single instant where you could point and say that's the moment it happened, because by the time any single instant in this sequence occurs, several earlier instants have already made it impossible for you, in any meaningful sense, to be there to experience it. It's a genuinely strange thing to realize that the question what happens when you touch a neutron star doesn't actually have a single answer, because touching turns out to be the very last and least significant step in a sequence that started acting on you long before contact was ever physically possible. The tidal forces did the actual work of ending you, thousands of kilometers out. The magnetic field and crushing density that follow are simply what happens to the raw material left over afterward. A kind of cosmic recycling process operating on matter that, by any meaningful definition, stopped being a person several thousand kilometers and a couple of seconds earlier. There's one more piece of this puzzle worth understanding, because it adds a genuinely strange visual dimension to everything we've covered, and it involves the sheer speed at which some of these objects spin. When a massive star's core collapses into a neutron star, it retains almost all of its original rotational momentum. The same physical principle that makes a spinning ice skater speed up dramatically when they pull their arms in close to their body. Try picturing that ice skater analogy at its actual, honest extreme though, because the usual classroom version of it dramatically understates what's happening here. An ice skater pulling their arms in might double or triple their spin rate. A collapsing stellar core doesn't just pull its arms in a little. It goes from a star spread across a diameter of hundreds of thousands of miles down to a sphere 12 miles across, a size reduction so extreme that the corresponding increase in spin rate isn't measured in multiples of 2 or 3, but in factors of hundreds of thousands or more. A star that might have taken weeks to complete a single rotation, spread out across a diameter of hundreds of thousands of miles, gets compressed down into a sphere 12 miles across, and that same rotational momentum, now concentrated into an object a tiny fraction of its original size, causes the resulting neutron star to spin dramatically faster, sometimes absurdly so. Think of it this way. If you took a spinning merry-go-round the size of an entire city block, with people scattered evenly across it, slowly turning once every few minutes, and somehow compressed that entire structure down to the size of a dinner plate while keeping all the same spinning momentum, the resulting object wouldn't just spin a little faster. It would spin so violently that fast stops being an adequate word to describe it, which is roughly the transformation happening to a star's rotation during collapse, just scaled up from a thought experiment involving a merry-go-round to an actual physical star weighing more than our own sun. The slowest spinning neutron stars we've observed complete a full rotation every several seconds, gradually slowing down further over time as they radiate away energy and lose rotational momentum to their surroundings. but some of the fastest spinning neutron stars ever detected complete a full rotation in a few thousandths of a second. The current record holder spinning at a rate of 716 times every single second, based on precise radio pulse timing measurements taken by astronomers using large radio telescopes. Picture that for a second. An object with more mass than our Sun, 12 miles across, spinning more than 700 times every second, fast enough that a single point on its equator would be moving at nearly a quarter of the speed of light, all while holding itself together against the same crushing gravity we've spent this entire video discussing. The outward centrifugal force from that spin, balanced by an inward gravitational pull so extreme it makes the spin, remarkable as it is, still not quite strong enough to tear the star apart. If you tried to spin an object built from ordinary materials, steel, concrete, anything humans have ever engineered, at even a small fraction of that rate, it would fly apart instantly. The material simply unable to withstand the outward force trying to tear it away from the center. A neutron star's own gravity is the only thing in the universe strong enough to hold something together at a spin rate that extreme, which is itself a small additional reminder of just how overwhelming that gravity actually is. Strong enough to keep a stadium-sized object from disintegrating even while whipping its outer edge around at speeds that would make our fastest human-made spacecraft look, by comparison, almost stationary. This spin is exactly why we're able to detect and study most of these objects in the first place. And it ties back to the pulsar discovery story from earlier, because a spinning neutron star with a strong magnetic field doesn't emit its radiation evenly in all directions. Instead, particles accelerated along the star's magnetic poles produce narrow, concentrated beams of radio waves and X-rays, and because the magnetic poles usually aren't perfectly aligned with the star's spin axis, these beams sweep around through space with every single rotation, exactly like the rotating beam of a lighthouse. When one of these beams happens to sweep across Earth, our telescopes catch a brief pulse. And because the star's spin is so mechanically stable, driven by something with the sheer physical momentum of a collapsed stellar core rather than anything as fragile as a mechanical clock, these pulses arrive with a regularity that rivals or exceeds the best atomic clocks human engineers have ever built. Astronomers have actually used the almost impossibly precise timing of certain pulsars to test some of the most demanding predictions of Einstein's general relativity, and to help detect gravitational waves rippling through the fabric of space itself, by watching for the tiny, telltale disruptions those waves cause in the otherwise metronomic timing of pulses arriving from deep space. This technique, called pulsar timing, works by monitoring dozens of these millisecond pulsars scattered across the galaxy simultaneously, essentially turning the entire galaxy into a giant natural gravitational wave detector. One built not from mirrors and lasers the way ground-based detectors work, but from the residual spin of dead stars, ticking away with a precision nobody expected nature to hand us for free. In a strange roundabout way, the same extreme spin that would make a neutron star surface such an unimaginably hostile place has also turned these objects into some of the most useful, most precise natural instruments available to modern physics, cosmic clocks built entirely by accident out of the wreckage of a star's violent death. I want to take a moment here, before we head toward the close of tonight's story, to actually sit with the full picture we've built. Because I think it's easy to let each individual piece, the tidal forces, the magnetic fields, the spin, the energy release, wash past as a series of impressive but disconnected facts, when really they all fit together into one coherent, almost unbelievable object. Picture the whole thing at once. A sphere no bigger than a modest city, spinning in some cases hundreds of times every second, its surface locked in a magnetic field powerful enough to crush the very shape of atoms into thin, rigid needles, radiating enough residual heat from its birth to glow at temperatures of hundreds of thousands to millions of degrees, all of it held together against its own crushing gravity by a form of matter that exists nowhere else in the observable universe. Packed so densely that a single sugar cube's worth would outweigh every building in a small city. Now layer the earlier part of tonight's story back on top of that picture. This same object, from thousands of kilometers away, reaches out with tidal forces strong enough to dismantle anything built from ordinary matter before it ever gets close. Its gravity bends light so severely that its own far side becomes visible from certain angles, folded around into view by the same warped space-time responsible for everything else we've discussed. And none of this is some rare, singular oddity dreamed up as an extreme edge case for a video like this one to explore. Based on how supernovae are understood to work and how frequently they occur across a galaxy the size of ours, astronomers estimate there are likely at least several 100 million to a billion neutron stars scattered throughout the Milky Way alone. The vast majority of them too faint, too old, or too poorly aligned with Earth to ever be detected by our current instruments, simply drifting through the dark in enormous numbers, spinning, glowing faintly, waiting in a sense that implies no actual intention, for absolutely nothing, because there's nothing out there to wait for. Picture the night sky the next time you happen to be somewhere dark enough to actually see it properly, away from city lights with a full spread of stars visible overhead. Every single one of those visible points of light is an ordinary, functioning star, still burning through its nuclear fuel the normal way, but scattered invisibly among them, outnumbering the stars you can actually see by a wide margin. Are these silent, spinning, magnetically violent remnants, dark to the naked eye, detectable only through the specific, narrow beams of radiation a lucky few of them happen to point in our exact direction? The night sky you think you're looking at is missing almost all of its most extreme residents entirely, hidden not because they're far away, but because they're simply not shining in a way your eyes, or honestly most of our telescopes, were ever built to catch. That number is worth sitting with for a second, because it reframes everything we've talked about tonight from a single exotic curiosity into something closer to an ordinary, if extreme, feature of the galaxy we happen to live in. Somewhere between several 100 million and a billion of these objects, each one an entire dead star compressed into a city-sized sphere, each one spinning, each one wrapped in a magnetic field that would casually rewrite the laws of chemistry for anything that got close enough, are out there right now, scattered across our galaxy, mostly invisible to us, mostly silent, mostly ignored by everything except the handful of astronomers dedicating entire careers to finding and studying the rare ones that happen to announce themselves through a lucky alignment of their radio beams. We are not talking about some singular, freak exception to how the universe usually behaves. We're talking about one of the more common endpoints for massive stars, repeated across our galaxy on a scale that's honestly a little dizzying once you actually stop to picture it. Consider that our own galaxy contains somewhere in the range of 100 to 400 billion stars total, and out of that enormous population, only a relatively small fraction. The ones considerably more massive than our own Sun are even capable of ending their lives as a neutron star in the first place. And yet, even drawing from that comparatively narrow slice of the galaxy's total stellar population, over the roughly 13 billion years our galaxy has existed, the accumulated total still comes out to several 100 million to a billion of these objects. A reminder of just how much time 13 billion years actually represents, and how many chances that much time provides for even a relatively uncommon event happening galaxy-wide to accumulate into a genuinely enormous final tally. And I think that's really the heart of what makes this whole topic worth spending an evening on. More than the individual gruesome details of what would happen to a human body that wandered too close. It's the reminder that extreme isn't a rare exception carved out somewhere at the very edge of physics, reserved for one bizarre object tucked away in some distant corner of the universe. It's happening right now in ordinary quantities, scattered by the hundreds of millions across our own galaxy, following physical laws that are the same laws governing the chair you're sitting in. The light reaching your eyes from this screen, the gravity holding your feet to the floor. Push those same laws far enough, compress matter densely enough, spin something fast enough, and the ordinary rules that make up your entire daily experience of reality don't get replaced by something new and different. They get followed to a conclusion so extreme it stops looking anything like the world you know, while still, technically, being the exact same physics the whole time. There's a version of this idea that applies closer to home, too. One that doesn't require imagining a neutron star at all. Every law of physics you've ever taken for granted, gravity, electromagnetism, the basic behavior of atoms, has a comfortable, everyday range where it behaves exactly the way your intuition expects, and an extreme range, usually far outside anything you'll ever personally encounter, where that same law produces results your intuition was never built to anticipate. Water is still water, whether it's a gentle stream or the crushing pressure at the bottom of the deepest ocean trench, obeying the exact same chemistry the entire time, even though those two environments could hardly feel more different to something living inside them. Gravity is still gravity, whether it's gently keeping your coffee cup on the table or crushing a stellar core into a neutron star, obeying the exact same equations Isaac Newton and Albert Einstein worked out centuries and decades ago, respectively, using nothing more than careful observation and patient mathematics. There's something worth carrying with you from this. Something that goes beyond the specific, admittedly grim details of tidal forces and magnetic field distortion we've spent tonight walking through. Every single one of us lives our entire lives within an incredibly narrow, comfortable slice of what the universe's physical laws actually permit. Gentle enough gravity to walk around without our bones crushing under our own weight. Weak enough magnetic fields that our own atoms hold their normal, familiar shape. Cool enough temperatures that chemistry, the whole intricate, elaborate dance of molecules that makes up every living thing, including you, including me, including everyone you've ever loved, can actually happen at all. We tend to think of these conditions as simply normal, the baseline reality against which everything else gets measured as strange or extreme. But they're not the default setting of the universe. They're an unbelievably narrow, unbelievably fortunate exception, carved out of a cosmos that's perfectly happy elsewhere and constantly, to run its laws all the way out to the crushing, atom-distorting, chemistry-erasing extremes we've spent this entire conversation exploring. Somewhere out there, in one of those hundreds of millions of neutron stars, gravity is currently 100 billion times stronger than what you're feeling right now. Somewhere else, a magnetic field is currently crushing atoms into needles thinner than anything a microscope on Earth could ever resolve. None of that is happening because the universe made an exception for those places. It's happening because those places are simply following the same laws you are, pushed out to a part of the range you never have to personally experience. You are not living in the ordinary state of the universe. You are living in one of its rarest, gentlest corners. A corner so narrow and so specific that it took 4.5 billion years of an entire planet's history just to produce a single mind capable of understanding how strange and how lucky that narrow corner actually is. Think about everything that had to hold steady, uninterrupted, for that corner to exist long enough for you to be sitting here listening to this sentence. A star stable enough to burn quietly for billions of years without collapsing into anything like what we've spent tonight describing. A planet at exactly the right distance to keep water liquid instead of frozen solid or boiled away. A magnetic field, Earth's own modest half-Gauss field, just strong enough to deflect the worst of the sun's radiation without ever coming anywhere close to crushing a single atom in your body. Every one of those conditions had to hold simultaneously for an uninterrupted span of time longer than most of us can genuinely picture, just to produce the specific, narrow set of circumstances that let something like you exist at all, let alone exist long enough to spend an evening thinking about neutron stars. None of that stability was guaranteed, and none of it is permanent either, though the timescales involved in it changing are, thankfully, far longer than anything you personally need to worry about tonight. But it's worth remembering, the next time something in your ordinary day feels chaotic or overwhelming, that you're experiencing that chaos from inside one of the most stable, gentle, atom-preserving pockets the universe has ever managed to produce. A pocket so rare that the alternative, the actual default behavior of matter under the universe's more common, more extreme conditions, would end you before you finished reading this sentence. Ordinary, boring, gentle stability turns out to be the rarest, most remarkable thing the universe produces, not the least. So here's what I'd like to leave you with tonight, and I mean this as something to actually sit with, not just a closing line before the outro music starts. Somewhere out there, right now, in the quiet dark between the stars you can see from your window, there are hundreds of millions of dead stars spinning at speeds that would tear apart anything built from ordinary matter, wrapped in magnetic fields that would unmake the very idea of chemistry, holding themselves together by a form of matter that exists nowhere in your entire everyday experience of reality. And none of that changes the fact that you, sitting exactly where you are right now, made of atoms that hold their gentle, familiar shape, breathing air that follows the ordinary rules of chemistry you learned about in school, are living proof that the universe, vast and violent and strange as it clearly is, also somehow found room, in at least one tiny corner, for something as improbable and as precious as a person who can look up at the night sky and wonder what it's all made of. I think there's a specific kind of comfort available in that thought, if you let it actually land. One that doesn't require pretending any of tonight's more unsettling details away. The universe doesn't need to be gentle everywhere to have been gentle here, in this one specific corner, for this one specific stretch of time that happens to include you. The same cosmos capable of crushing atoms into needles, capable of spinning a city-sized sphere 700 times a second, capable of releasing more energy in a fraction of a second than our sun produces across 100,000 years, is also apparently capable of holding a single quiet evening together long enough for you to sit somewhere comfortable and think about all of it without any of it reaching you. That's not a small thing. Given how much of the universe operates at the extremes we've spent tonight exploring, the fact that any of it ever holds still long enough to produce something like an ordinary evening is, in its own quiet way, one of the more remarkable things reality has ever managed to do. It's a strange kind of gratitude to feel, honestly, gratitude toward physics itself, toward the specific, narrow set of conditions that happened to hold steady long enough to let atoms stay round, let chemistry happen, let a nervous system develop complex enough to eventually sit here and marvel at all of it. But I think it's a gratitude worth actually feeling, every once in a while, rather than something to only notice by contrast, only after spending an evening walking through everything the universe does to matter when those gentle conditions aren't present. The ordinary feels ordinary precisely because you've never had to compare it to anything else. Tonight, hopefully, gave you something to compare it to. If tonight's story gave you a genuinely new way to think about what extreme actually means, I'd love to hear it. Drop a comment and tell me honestly, now that you know the real answer, whether your gut guess about the pain was right. And while you're there, tell me which detail actually stuck with you the most. The sugar cube weighing as much as a mountain, the atoms getting crushed into needles, or the fact that there are hundreds of millions of these things quietly spinning through our own galaxy right now. I read every comment, and honestly, watching which specific detail lands hardest for different people is one of the most interesting parts of making these videos. Some people get stuck on the density. Others can't shake the image of atoms turning into needles. And a surprising number of people, every time this kind of topic comes up, end up telling me it's actually the sheer number of these objects, the hundreds of millions quietly drifting through our own galaxy, that unsettles them the most, more than any single gruesome detail about what would happen up close. There's no wrong answer here, and honestly, the fact that different details land differently for different people is exactly why I keep asking. If this is the kind of thing that makes you want to see the universe a little more clearly, subscribe, because there's a lot more of exactly this waiting. And until next time, take a second before you go and just notice how strange it actually is that your atoms get to be round. That roundness, the ordinary, unremarkable, familiar shape of every atom in your body, holding steady right now without any effort on your part, without any conscious thought, without you ever having to ask it to. is the entire difference between the world you're sitting in tonight and the world we've spent the last several thousand words describing. It's easy to walk past that fact without ever noticing it, the same way it's easy to walk past clean water, or breathable air, or a sky that isn't actively trying to crush you. But every single one of those things is a condition, not a guarantee, held in place by a specific, narrow, and genuinely rare set of circumstances that the rest of the universe, left to its own devices, doesn't particularly care about maintaining anywhere else. Tonight, you got to spend a little time looking at what the universe does when it isn't maintaining those conditions, out there in the dark, on objects too far away and too extreme to ever actually threaten you. And then you got to come back, atoms still round, chemistry still intact, to an evening that, by the universe's own usual standards, is quietly, almost unbelievably, one of the rarest things it has ever produced. Not because rare, gentle evenings like this one are cosmically significant in some grand, universal sense, but because they're statistically improbable, tucked into a narrow window of physical conditions surrounded on every side, at every scale, by matter behaving in ways that would end them instantly. That contrast, more than any single fact about density or magnetic fields or spin rates, might be the thing actually worth carrying out of tonight's video and into the rest of your week. We'll pick this thread back up again soon, out among more of the universe's stranger corners, because there's always another one worth exploring. Another object out there quietly doing something to matter that our ordinary, everyday intuitions were never built to anticipate. Until then, take care of that roundness. It's doing more work than it ever gets credit for. And if you find yourself lying awake tonight thinking about sugar cubes weighing as much as mountains, or atoms crushed into needles thinner than anything a microscope could ever resolve, that's not a bad thing to be thinking about. That's just what happens when you spend an evening looking honestly at how strange the place you live in actually is, and then remembering, quietly, gratefully, that you happen to live in one of the rare corners of it gentle enough to let you notice. There are worse ways to fall asleep than that, and honestly, there are worse things to be a little bit obsessed with than the actual, honest, measured scale of the universe you happen to call home. Thanks for spending this evening on it with me, and I'll see you in the next one. Atoms still round, chemistry still intact, ready to go, looking for the next strange corner of this universe together, wherever the physics happens to take us next, because there's always another one waiting, quietly, out past the edge of what feels ordinary, further out than you'd expect, and stranger than any of us could have guessed before someone actually bothered to do the math. That's really the whole job of this channel, in the end, not to invent the strangeness, but to find it, already sitting there in the equations, waiting patiently for someone to translate it into something you could actually picture, and then hand it to you, whole, honest, and hopefully a little bit unforgettable, the same way tonight's sugar cube, and its billion tons, and its atoms crushed into needles will hopefully stick with you long after the video ends, popping back into your head at some unexpected moment weeks from now, the way the strangest facts always do, uninvited and completely welcome. See you then, out among the next strange thing waiting to be measured, explained, and finally properly understood. The way this entire evening started with a single sugar cube and ended somewhere out past the edge of everything you thought you knew about what extreme could possibly mean, which, if tonight did its job right, is exactly where a good story about the universe should always leave you. A little smaller, a little stranger, and somehow a little more grateful for the ordinary. Which, when you really stop to think about it, might be the single most valuable thing any of these videos ever manages to leave you with. That and a sugar cube you'll never look at the same way again, sitting in a bowl on a kitchen counter somewhere looking perfectly ordinary, hiding, in its own quiet way, one of the strangest numbers the universe has to offer, waiting for someone to remember, next time they reach for it, exactly what that kind of density would actually mean, and just how far the ordinary world you're standing in really is from the extremes we spent tonight exploring together. And how strange it is that both of those worlds, the gentle one and the crushing one, are running on the exact same rules the whole time.